Hey everybody! So I wanted to make a quick video to discuss what you do when you get to a test or a quiz or a homework problem and it's a buffer and you're stuck and you're like, oh god, I can't do anything. Yes, I am making this video because of the midterm that I have created this weekend, and it seems like a lot of you were stuck on a buffer problem. So the problem we're looking at, if we were doing the problem from the exam, and I'll just use the same numbers. We know that we have, well, we want to make 250 milliliters of a 0.2 molar total concentration buffer using 0.4 molarity weak base and 1.0 molarity strong acid. It so happens I've got to get something. The weak base we were using, I give it as the, hold on. So the weak base that we're using has a pKa of 7.43. Right, so I didn't even make you convert it to a pKb. So what do? Let's say we get to this and we just have no idea what to do. We look at it and we say, okay, I don't know what to do. Well, the best thing you can do is, the best thing you can do is just start with the basics, right? Start with the simple things. You know that you're making a buffer, you're going to have a solution that's 0.2 molar total concentration. Let's, instead of doing the buffer, let's just do a titration. Now this problem isn't a titration problem, but titrations are something we should be really comfortable with. Oh my goodness, what do? So let's just say we're going to have some titration curve. That's going to be pH equals 7.43. And then we figure out what volume that is, right? We just do our typical points. We do midpoint, volume to midpoint, volume to equivalence point. We just do those simple things, then we see what kind of information we can get from those simple things. The volume to the equivalence point is usually the one I start with. That's going to be 250 times 0.2 equals moles of buffer. We'll just call it moles of system. Right, that's going to be the system we create. And then I'm going to take my moles of system divided by 1 molarity for my titrant. And that will give me, since I left it in milliliters, this is going to give me milliliters to equivalence point. So it's going to be 250 times 0.2. I have a calculator someplace around here. Okay, so we do 250 times 0.2. That's going to give us 50 milliliters. Right, so right away, we got a couple things. It's 50 mils to there. It's 25 mils to there. And the middle is a pH at 7.43. Now, this gives us an idea of what kind of buffer capacity we'd expect. We expect something less than 50 mils. We expect any pH in this range is going to be something less than 50, and then depending on where it is relative to the midpoint, we can tell whether it's going to be above a pH of 7.43 or below a pH of 7.43. For this particular problem, we said we wanted to make a buffer at a pH of 7.25. So we're expecting something over here for a pH of 7.25. Oh god, good grief. No. this is a weak base. I want to be at a lower pH, not a higher pH. I'd expect something over here. So I'd expect, in order to make the buffer, I'd need somewhere between 25 and 50 mils, probably closer to 25. That gives us a ballpark of what we'd expect. Clearly, it's not exactly the right answer, but it gives us an idea of what to expect, and it gives us a starting spot for thinking about things. And on an exam situation, it gives us a lot of partial credit, just realizing how we can think about the system. Part B is what's the buffer capacity. And we can think of the capacity in terms of kind of two different parts. Right? We can think of the capacity, it's going to be from about here to about here. And we know that it's got some 1 to 10 ratio, so let's say 10% reacted to 90% reacted. Now, that's not exactly the right answer, but it gives us, again, a good ballpark to think about what we're doing. So if I think of 50% is all reacted, 5 milliliters would be my 10% reacted. I'm just doing, here, let's do this. We'll actually do the math. I'm going to do 50 times 0.1 goes to 5 milliliters, would be my 10% reacted. And then I would do 50 times 0.9. That's going to give me 45 milliliters. Notice, take the difference. That's going to be the approximate buffer capacity. We can say it's something like 10% to 90%. That should be in the right ballpark. Again, it's not exactly the right answer, but it gives us a way to kind of frame and think about things. And it turns out that the right answer is shockingly close to 40 milliliters. It's about 41 milliliters is the actual right answer. So even with this rough approximation, you can get really close to the right answer, but more importantly, you can demonstrate some understanding of the stoichiometry associated with the pH changes, right? And you can get that information communicated. Part C, which was changing the original buffer by adding 4 milliliters of 1 molar sodium hydroxide. This would be like, instead of adding approximately something like 25 to 50, let's say 32, that would be essentially moving us backwards a little bit. And the problem is, without having the exact value in here, we don't know how far back we're moving, but it again gives us some kind of idea. Part C would be really difficult to do with approximations because you're approximating on an approximation now. But you can still get an idea that because you're adding sodium hydroxide, the pH goes up. And you can get the idea that it's going to be someplace pretty close to the midpoint, actually. If I remember correctly, you get something that's just before the midpoint, but to know that for sure, we'd have to actually do the stoichiometry and do the equilibrium. Hopefully this gives you some context to think about the next buffer problem you run into.